All right, everyone, please take your seats. We'll get started on oral session 2. This is the third 369-3. And our first speaker is Lachlan Marnoch, who will, is ready now? Okay. So Lachlan, please take it away.
How can I get my slides? All right, good afternoon, everyone. Yorobul Nanyanghaseyo. My name is Lachlan Marnoch. I'm a PhD student at Macquarie University in Sydney in my second year, with my supervisor Stuart Ryder and Richard McDermott. I'm also associated with Astro 3D and CSIRO, and I work on FRB follow-up with Craft. So I'm mainly engaged with the optical and the infrared side of things, particularly with imaging. So as you might know, Craft is very good at localizing FRBs to host galaxies, often at relatively high redshift, which means that we need deep optical images of them, such as these ones. This is our current zoo of FRB host galaxies, as imaged mostly on the ESO Very Large Telescope and processed by IAUS369. And you're going to be seeing a lot more of these, thanks to Cracker and FRB. So Keith Bannister has already talked to you about Cracker, which is the Craft Coherent upgrade, and with which we're expecting to localize about 1 FRB per day to its host galaxy, which is a lot of host galaxies. And to try and keep up with that, we currently have an ESO large program in place at the VLT with the name FRB, with which we aim to create an unbiased sample of 50 FRB host galaxies with imaging and spectroscopy as well. And you can see some of our early efforts here on the right. Let's test this out. Yep, wonderful. But today I'm here to talk to you about what I've been doing with some of our older optical data. And that's to do with halos, or the circumgalactic medium. So halos were formed from the collapse of dark matter in the early universe, and they brought baryons along for the ride, which of course drove galaxy formation, with around 10% of this gas cooling and accreting to form halos at the galaxy centers. But much of the rest is still out there in the halo or the circumgalactic medium, and there are still many questions to answer about it. Although the gas in cluster halos is hot enough to be observed in the X-ray, the lower mass and variable temperature of galaxy groups and individual galaxy halos makes it hard to see. And much of this gas is believed to be in a hot diffuse state around 10 to the 6 Kelvin, which is difficult to detect in absorption or emission, but of course we know FRBs offer a very sensitive probe to this kind of material. Which means that FRBs have the potential to tell us a great deal about galaxy-scale halos. However, to get the most out of an FRB's potential as a halo probe, we want it to traverse not just the halo of the host galaxy and the halo of the Milky Way galaxy. We would also like it to cross a foreground halo, the halo of a foreground galaxy. And although most FRBs are expected to at least touch some foreground halos, close intersections are expected to be relatively uncommon, at least for individual galaxies. But some will cross halos by chance, and with these, we'll be able to complement the other probes of the circumgalactic media and enhance our understanding of baryons and halos. But this does require good localization, and preferably a known host, which is, of course is where Craft comes in, so that we can understand as much about what an FRB has touched on its way to us as possible. So there are 2 confirmed close intersections currently present in the literature, as far as I can tell, of which FRB 181112 is especially interesting. It was a Craft FRB that was found to cross the halo of a massive galaxy in the foreground and placed surprisingly low limits on its magnetic field, density, and turbulence. And this work was led by Xavier Prochaska, who was giving a plenary lecture later on Thursday, and we've been borrowing extensively from the methods used in his paper, Prochaska et al. 2019, as well as from Simha et al. And Sunil, in fact, spoke earlier on a similar topic. Yes, there we go. It's oh, here we go. All right. And that brings us to the one I'm interested in, which is FRB 1907-14, which is another Craft FRB with some previous work done on it already, as you can see here. So when we want to get a spectrum of this host with FORS2 on the Very Large Telescope, that's this galaxy here, we place the slit not just across the host, but also across this nearest neighbor in the sky, just on the off chance that it was in the foreground, and it turns out that it was. It's a much closer redshift of 0.08, which gives it an impact parameter of around 11 kiloparsecs to the FRB, which I believe to be the smallest confirmed impact parameter on record. I might be wrong about that. But yes, and from the photometry, this does indeed appear to be a dwarf galaxy, hence the title of this talk, with a stellar mass of around 10 to the 8.2 solar masses, which would make FRB2022 the first FRB to closely pierce a dwarf galaxy halo, which is interesting because halos on this scale are A, difficult to probe, and B, sensitive to models and feedback scenarios. So what we were hoping to do at the outset of this project was to conduct a straightforward analysis of what the DM, RM, and the scattering of this burst could tell us about the foreground galaxy and its halo. Much as Prochaska 2019 did for FRB 181112. However, this sightline turned out to be a lot more complicated than we bargained for. So we also obtained Muse follow-up of this field, and you can see some of the galaxies there. And with this extra data, we identified another 5 foreground galaxies, another 5 galaxies between us and the host, which is exciting, but also somewhat vexing. So, we want to, of course, to understand how our foreground halos contribute to the FRB dispersion measure, which means modeling them somehow. And Sunil has already spoken on very similar methods, so I won't go over them again. But suffice to say that using a modified Navarro-Frank-White profile, we estimate the dispersion measure from each individual halo. And from these Muse galaxies, that sums to about 86 parsecs per cubic centimeter. However, after accounting for all of the other DM components, this still left us with about 75 parsecs per cubic centimeter in excess of what we had modeled, even with what I think is quite a generous DM host allocation. And, as you can see, there are a handful of galaxies that loom rather large in the Force 2 imaging here, which were outside the Muse field of view. So we supplemented the Muse redshifts with photometric redshifts, which are of course less reliable from PS1 Storm, but sufficient to get a reasonable idea of what's going on in the foreground. And as if we didn't have enough foreground galaxies, we identified several more within the Force 2 field of view, including those ones that I pointed out before. And following the same method, but using these photometric redshifts, we estimated the DM contribution, and although most of the ones we identified don't contribute, according to the models, 4 of them seem to, and one of them, that would be H here, seems to be the greatest contributor. So, the DM of this FRB as measured is 504 parsecs per cubic centimeter, and we estimate all the pieces of it through various means, some of which you'll be familiar with. Adding all of this together, we can essentially account for the entire observed dispersion measure of this burst. That is with a relatively, again, generous DM host contribution, but not unreasonable one. And we can also see, as modeled, and Sunil actually has already talked over this, the sightline is quite overdense compared to the cosmic expectation value. There's one little twist though. So as you might have noticed, oops, that's the wrong button, this one. There's a bit of a cliff here in the DM, and that's because of a set of halo models that are at a relatively that are at a similar redshift at z equals 0.21, which might represent a galaxy group in the foreground. So to explore this, we estimated the group's mass from peculiar velocities, fed it to another MNFW profile, which this time represented the intra-group medium of the group, which could be a contributor. We obtained the DM estimates, and even considering this sort of separately to the individual galaxy halos, the IGRM here could plausibly close our DM budget, which is interesting. Adding it in, we could adjust DM host to accommodate for the lower value if we mixed it in with the individual galaxies. But if this is indeed a group, we might need to consider the model parameters a bit more closely. So there's still a bit of work to do, as shown here. Maybe with some of it, we might be able to zero in a bit further on certain halo properties. I still have some hopes to use the scattering to constrain, or the lack thereof rather, to constrain the turbulence and density of the CGM of the dwarf. And I would love to be able to contribute to the questions of whether dwarf galaxies have expelled baryons in their halos, which some models do predict, and distinguishing between different feedback scenarios. I still have high hopes for constraining these for our dwarf. However, ideally for foreground halo studies, it turns out, the sightlines would be underdense except for the halo of interest, which is kind of what happened with FRB 1811-12. So we need a large number of localized FRBs to cherry pick the interesting ones, which of course Krakow and FRB will help with. Yes, so in summary, halo gas in the circumgalactic medium is important to understanding galaxy feedback, and FRBs can provide unique probes for this. FRB 1907-14 is one such FRB. It penetrated several foreground galaxy halos and may be the first known to cross a dwarf galaxy halo, and may also have crossed a group halo, an intragroup medium. We estimated the DM contributions and still hope to constrain turbulence with scattering and possibly even the MNFW model itself. And I'll leave you with my summary slide. Thank you for listening to my talk.
Okay, we have time for questions. Please come up to the microphone or post them on Slack. I see some typing on Slack, but no questions. It may emerge.
I'm happy to answer them offline.
Okay. Well, thank you very much, Lachlan.
Thank you.
And our third speaker of this session is Kaitlyn Shin, who will present on Inferring the FRB Distance and Energy Distributions with CHIME FRB.
Hi, everyone. I'm Kaitlyn. I'm a grad student at MIT working with Kiyoshi Mitsui and the CHIME FRB collaboration. And yay, my slides are up. And I'll be telling you today about some populations analyses we did with the first CHIME FRB catalog. So, as I'm sure many of you are well aware, the CHIME FRB collaboration released our first catalog last year of 536 FRBs. And you can see on the sky map that's plotted here, the sample includes bursts from both repeating and apparent non-repeating sources. And for each burst that we have released in this catalog, we also have observed and measured properties such as fluence and DM. And so with this, we have the first statistically large sample of FRBs detected from a single survey. And it becomes interesting to try and ask populations level questions about these FRBs. And so what I'm going to be talking about today is work done fitting a joint fluence DM rate distribution of FRBs to this catalog 1 data. And as a brief aside, I want to mention that a lot of this builds upon the initial populations analyses we did in Catalog 1. We use the same statistical sample selection, and we also use the same formalism used to fit the model to the data. But the key difference is in the initial Catalog 1 analysis, when we fit for our fluence DM distribution, we assumed that the distributions in fluence and DM were entirely factorizable, which of course isn't particularly true as both fluence and DM encode distance information in some way. And so that's why we're using a more physically motivated model, and this model is actually developed by Clancy James et al. For their ZDM papers. And so this rate fluence DM distribution depends on 7 free parameters Q. And you can see there's like 2 main ingredients that I've underlined in different colors. So the underlined in blue contains information about the energy distributions, and underlined in orange contains information about the distance distributions. And I'm just going to briefly go through what some of the key components of each of these ingredients are. So, and the first ingredient with the energy distribution information, so it has contained within the spectral index, and we also assume a Schechter energy function where it's parameterized by gamma for the differential power law index and a characteristic exponential cutoff energy. And that it also includes a model for the evolution of FRBs with the star formation rate, where we're assuming smooth scaling with the star formation rate, smooth power law scaling with the power law index n, and phi naught is the volumetric rate at z equals 0 of bursts per cubic gigaparsecs per year. And the free parameters in the second main ingredient to this model come from the modeling for the host DM distribution, which we model as a log normal distribution, and that's parameterized by these two values, mu and sigma, right over here. So we want to take this R of FDM distribution, and we want to, fit that model to the data, and we want to answer all these interesting questions about FRBs, like what are their energy functions or their volumetric rate. But when we try and answer these questions, we have to be really careful to account for the observational biases. If we really want to try and learn about the underlying intrinsic FRB population. And so that was fortunately done with the injection system, where CHIME FRB injects synthetic pulses into the real-time detection pipeline to try and characterize our telescope sensitivity and selection effects. And for much more on that, you should check out Marcus Merrifield's e-talk. And so through injections, we're able to get the selection function of our telescope, which is a non-factorizable distribution of many parameters like fluence and DM. And so there's a lot of subtleties involved when you use these injections to calibrate out the selection effects while you fit the model to the data. I know that's a mouthful, but we've thought a lot about it. And if you have any questions about that, you should feel free to come and find me afterwards. So after taking into account all these selection effects and moving parts, we obtained this model fit for this R of FDM. And so shown here, on the left is the observed catalog 1 data, and on the right is our model prediction. And you can see that the data is entirely consistent with being the model plus some Poissonian noise. So to get these results, we did a full MCMC sampling of a Poissonian likelihood using uniform priors, and these are our full results. It's a lot, so these are the corner plots, and then this is a table with the best fit results. And when I say best fit results, I'm quoting the median of the posterior distributions with 68% uncertainties. And this is a lot to take in, so I'll just go step by step, break it into chunks. So focusing here on the first part, the energy function part. So what I've plotted here, all these white lines are allowable samples from my MCMC, and overlaid in blue is the best fit. And so this is the energy function scaled by the energy and the volumetric rate, plotted against the energy. And so we notice a few things. First, well, I guess first is if we want to quote a volumetric rate, we have to make sure that we are quoting it above a pivot energy, otherwise we would diverge at lower energies. And so we choose this pivot energy to be about 10 to the 39 ergs, and that gives us a volumetric rate of nearly 10 to the 5 gig bursts per cubic gigaparsec per year. And then we also obtain a slope of the differential slope of the gamma function. This differential power law index for the Schechter function of about minus 1.3, and characteristic energy cutoff that seems pretty well constrained at about 10 to the 41 ergs. And I guess as a brief aside for any of you who checked out Clancy James's e-talk or remember the table of values from Sean's talk earlier, I did a quick check, and actually all these values are consistent within, entirely consistent within error bars. So that's pretty neat. The next part I'm showing is I'm plotting the evolution of FRBs with the cosmic star formation history. So I guess the previous slide was a bit more to do with observables, and this is a bit more model dependent. And so again, in white are all the allowable samples, and you see there's just a lot more allowed. And then in blue is the best fit. In orange dashed n equals 0, that implies there's no tracing the star formation history. And then n equals 1 assumes a perfect trace of the star formation history. And so, while our value does appear to be closer to n equals 1 than n equals 0, if you just look at all these allowable chains, I would say that our data don't hold much constraining power for this power law index n. And similarly, for the host DM distribution, again, there's a lot of allowable distributions, and they seem to be all over the place. But the median value we do get for the host DM contribution is about 85 parsecs per cubic centimeters. And that's more or less consistent with a lot of, plus 70, minus 50 parsecs per cubic centimeter. So within error bars, it's pretty consistent with a lot of host DM values that have been used in literature. But both this distribution and the previous ones, they're not that well constrained. And perhaps this is unsurprising considering we didn't use any redshift information when we fit this model to the data. But with upcoming instruments like CHIME FRB outriggers, we might be able to expect a lot more redshift information for FRBs. And I mentioned CHIME FRB outriggers specifically because the neat thing with this model and this formalism that we can do is we can predict an observed redshift distribution for what CHIME FRB outriggers might see, because CHIME FRB outriggers would have the same observation triggers as CHIME FRB. And so you can see here that this observed redshift distribution peaks at about a redshift of 0.4, and most of the area of the curve is below a redshift of 2. And so this seems to suggest that CHIME FRB outriggers, the bursts that they would see, might not be that useful for high Z cosmology, for example, but applications like lensing, totally fair game. There is one caveat that I do want to mention though, and that is I breezed past this way earlier, but I mentioned that this entire study was done using the same statistical sample that we used as the initial populations analysis, and that means that would exclude bursts such as lower signal to noise bursts because we wanted to make sure we were complete. So it is entirely possible that we would detect, or that this distribution would change slightly when you include information like or that this might change or might not be totally faithful if you think about the CHIME FRB detection of lower signal to noise bursts. So yeah, just to sum up, we fit a 7-parameter model, a joint rate distribution of fluence in DM. I just heard the timer go off. So I guess I'll leave my conclusions here, and this has recently been posted to the archive, so if you have any questions about some of the more nitty-gritty details, definitely check that out. Thank you.
Thank you for keeping the time. We have one question online which I can relay. So the question of repeaters and how that affects the sample and the statistical properties.
Yeah, so the statistical sample ended up being 271 bursts out of the 536. And there are a variety of cuts that we used. So low signal to noise, we excluded bursts detected on pre-commissioning, so on and so forth. For repeater bursts, what we did was to minimize our, observational bias to repeating sources. We took the first burst from each repeater that we observed. So because it's like if you take the brightest one, you would bias towards the brightest. Anyways, but if you're unhappy with that, those sources actually, when you take all the other cuts into account, only make up 5 out of the 271 samples. So it wouldn't significantly affect the results either way.
Great talk and wonderful results. Coming back to the injections, if I can ask one question on that, will you be providing the outputs from those simulations so that folks can do analyses like these for themselves on the CHIME data set, and how?
Yeah, so with Marcus's paper posted on the archive, he's also released the injections data set as well as a really nice tutorial for using and accessing the injection system. So yes, definitely check that out as well.
Okay, let's see here. Clancy James has a question on Slack about the value of DM halo and Milky Way contributions and what model you use for those.
I got to use a bonus slide. So for Milky Way halo, I think I fixed it to 30 plus 50. 50 being the average DM NE 2001 contribution, and 30 just based on other values people did with similar analyses, such as Pragya-Chawla's DM scattering paper. So that was for the halo, and then for the DM Milky Way, or actually, yeah, no, sorry, I'm mixing them up. But anyways, sorry, I'm still a little jet lagged. So what we did check our sensitivity to the assumption of DM Milky Way that we made. So I think our our fiducial value was 80 parsecs per cubic centimeters, but we did repeat this analysis for DM of Milky Way 50, 60, 70, 90, 100, in those intervals of 10. And you can see here that these results are, they're, what I can confidently say is the statistical uncertainties are larger than the uncertainties provided by this the variance in this DMMW assumption. And so with that, we just proceeded with DMMW equals 80.
Okay, thank you. We'll have to wrap it up there. So let's thank our speakers all. And that concludes the third session, and we'll transition to... Thank you all. And so please bring the discussion and questions to the Slack channel, IAUS Breaking News. And now we'll transition to the discussion proper with our panelists who are available on Zoom. And in this, sorry, there's some in the room. Oh, and some in the room also. And we'll try to make this work in a hybrid format. But in this case, this discussion is really in the context of cosmological uses of FRBs as probes and structure of the universe. As your chair and host, I am I'm here to try to stimulate some discussion as best we can. Oh, we do have slides. Who's she? Oh, okay. So shall we? Yep. Okay, we'll pass it off to people online.
Super. Thank you.
Yep. Thanks, Keel.
Recording in progress.
Yeah. So I think mostly Jenny and I threw together some prompt slides. Jenny, you made the intro slide. Do you want to sort of kick us off, I guess?
Well, I just said the topic is theoretical applications, but on the other hand, we also have observational feasibility. So what we have to see what are feasible applications and how precise and accurate can we get with the different topics that we listed. For instance, with the dispersion measure over redshift, or the baryon cross power spectrum, and the multiply imaged FRBs. So we saw these three main applications of FRBs for cosmology. And then we would like to discuss in how far all these applications have systematic issues and also have statistical issues that we should tackle in order to get the most precise and accurate estimates for our results.
Great. So I guess the first thing we wanted to talk about was, the DM versus Z. We heard a lot about this today, which in the context of the Hubble parameter. So I have, and there's a bunch of discussion about this on Slack already today. So we have this very nice measurement that was, a 10%-ish, 10 to 15%-ish measurement of the Hubble parameter that comes from the second equation here, where the DM that we observe should be inversely proportional to the Hubble constant. And there's a bit of, so my primary concerns are, will this ever reach a precision where it is informative of, say, the Hubble tension, right? Where you really need to get down to few percent measurements, to have, a 2 to 3 sigma, discern between sort of the shoes measurements and the CMB measurements. You need sort of 2 to 3% measurements of the Hubble parameter. And my, there's two things here that I think are, even with infinite FRBs that are just very degenerate with that, which is this FIGM number has to be independently measured. And you might worry that, and that's perfectly degenerate because it multiplies the Hubble constant. And then there's the DM host has a different redshift dependent if the DM host itself is not redshift dependent. However, there's no reason there's no a priori reason why the host contribution, here I'm including the host and the circumburst environment, sort of like the inner few parsecs, there's no reason that couldn't be redshift dependent as well. So I'm very concerned that that DMZ will not ever be informative of the Hubble parameter. But I think there are different opinions, certainly on Slack. There's some discussion about that earlier, and I'd like to hear more opinions about that.
Okay, yeah, okay. I think for the H0 problem, it is, it is a simple way to put as a discrepancy of one parameter. Oh, by the way, this is Injima here. But I think the deeper problem is that, in principle, there could be a problem of cosmology. There was paper of analyzing different mechanisms to reconcile the tension of H0 for both the high redshift and low redshift. And it is become gradually clearer that you cannot just simply modify low redshift physics to reconcile that H0. So in the future, there could be a dramatic change of, in principle, there could be some dramatic change in cosmology to modify physics at both high redshift at a very early time and the low redshift. So yeah, so that is something to keep in mind. So maybe at some stage our whole formalism should be changed. Yeah.
I agree. And I have another thing that always makes me wonder when we see these H0 tension. We are not only probing different physics, we are also probing very different scales with all the different probes. For instance, if we have supernovae, they are point-like sources and they travel through the universe in the optical redshift, in the optical bands. Here we have the electromagnetic, the gas part. And on the other hand, we can also have the quasars, which should be similar to the supernovae probes for strong gravitational lensing. But on the other hand, they have a broader emission profile. So they probe different scales when they travel through the universe. And I think maybe the tension comes from the problem that we should also take into account these different peculiarities of the propagation of the sources. What do you think?
So is that a suggestion that's an astrophysical peculiarity, that some effect that we're not considering, or that there's a new physics that's causing this?
Yes, I think it's systematics, if you want to call it like this, because I think if you have the supernovae, they are really more or less point-like sources. FRBs are even more point-like sources, but AGNs have a broader emission profile. And if these light beams propagate through the universe, they hit the substructures in a different way, and different effects have to be taken into account. And I think that propagation of light or any electromagnetic radiation through a clumpy universe is not totally understood. That's my gut feeling that something might be going on there.
Could I relay a question from Slack? So Clancy James asks if the panelists can comment on prospects for reducing the uncertainty in FIGM, because this is a big systematic for H0.
I think on Slack earlier, Dave was the most knowledgeable, right? So my understanding is this comes from, so maybe he can comment, but my understanding is this, basically you do 1 minus everything you can count, right? And everything, because everything you can count is like 15%, you're allowed to be off by 30%. Have 30% uncertainties on it, and and still only have 5% uncertainties on 1 minus that number, which that's a compelling argument, but I don't know how good these syntheses can really get, and how do you get that 30% number down?
I think so. I saw this question before. This is a big factor of uncertainty if we want to determine H0. So in the future, if we want to kind of pin down what's really F as a function of Z, you will need to have a 3-dimensional distribution of structures that showing how really that light ray goes through. In which case, we would need a 3-dimensional information, things like future DESI or maybe Euclid and such, to tell us a fully decomposed diffuse gas distribution, and also things like gravitational potential and so on, to fully decouple this term from H naught, and that is what I think. And I think the future fruitful data from three-dimensional galaxy survey or 21 centimeter survey will help us on this. Yeah, thank you.
Any other comments in the room on this slide? I don't see any. Kia, would you like to proceed?
Sure. Yeah. So yeah, I guess we can go. So I'm pessimistic about this because I see one free function that I can measure on the left and two free functions on the right that I have to model, and the informatics don't quite work out for me. But maybe we can do better. But yeah. But something I am super pumped about is the baryon power spectrum. So this one was this slide was also mine, one of the main ones I wanted to talk about. So this is a forecast by Matthew Metahavachuril and a bunch of folks at Princeton, and they like to think about the kinetic Semyonov-Zeldovich effect. We've actually been alluding to this this whole conference, saying that the FRBs can inform the missing baryon problem, not whether or not they exist, because we know they exist, but exactly where they are. Are they in voids? Are they in filaments? Are they in puffy halos around clusters, so on and so forth, right? This framed in this light, where you measure, the detailed statistic you measured is the power spectrum, like the galaxy power spectrum or the matter power spectrum that we measure all the time in cosmology, but in this case, it's the baryon power spectrum as traced by the electrons. And that is, like, I think, one of the most quantitative ways that you can solve that missing baryon problem, that you can really measure, where in the universe they are. And it turns out, I think this is, important for, so I think this is intimately doable, right? This, this forecast was actually very conservative, and, so, an instrument like CHIME FRB outriggers, or even the coherent ASCAP could do a measurement like this. And I think, and it's actually super important measurement to make. So in this paper, they talked about breaking this degeneracy with the KSZ, so you can use it as a cosmological probe. There are also, there's a nice recent paper where the introduction was really nice by Nicola et al. That talked about how important it is to get a handle on where the baryons are for weak lensing, because these baryons, after all, are all the baryons in the universe, or 85% of them, and really understanding their power spectrum, it reduces a key systematic and weak lensing, which is thought to be our main. The way that we are going to, that the community is going after dark energy, and then of course the biggest problem in galaxy formation, one of the biggest problems in astrophysics is feedback, right? We don't know exactly how feedback works. All the simulations get feedback wildly different, and this quantity, this power spectrum, is hypersensitive to feedback models, right? This is, the feedback just tends to push baryons around in very violent ways. And so this is, I think, one of the most interesting measurements that you could make in much of astrophysics, because you might argue that just solves feedback, right? Which is, a very lofty claim, but solving feedback would be the best thing, right?
Okay, Q, I wonder, the second data is the CMB state flow across DESI KIZ. So clearly that is KIZ. But for the first one, does this much Havishai cross-correlate FRB directly with DESI galaxy distribution or KIZ, or what it is? Yeah.
You cross-correlate excess DM, so you take the DM of every FRB, every background FRB, subtract off the McCart expectation, and that gives you excess DM, which includes contributions from from the host, the circumverse environment, and the large scale structure in the universe. So sometimes it will even be a negative number, right? Because along the line of sight, there'll be a giant void. And you cross-correlate that with galaxy positions. And because you're cross-correlating, this is completely immune to biases from the host, right? I mean, you don't care that the host DM contaminates the excess DM measurement, but doesn't correlate with the foreground galaxies. And so you get to measure this power spectrum with, I think, is very, very robust to systematics. I don't see, I've thought about this for, for quite some time, and I can't think of how this breaks.
So by these statistics, you assume that you can subtract the background FRB in some sense, or mean FRB value. I mean, you would work on the fluctuations of DM from those FRB, right? In that sense, you would need to assume a pretty reasonable size of the FRB catalog to do that correlation, right? Yeah.
This forecast is for 10,000 FRBs, but for a variance of the host DM that's much higher than the most recent estimates. So I think you could do a very good, sort of 10% level measurement with 1,000 FRBs, which is, ASCAP, CHIME FRB, that's only a few years on. Oh, with redshifts, you need redshifts for every one of them, but we will have that. Right?
Sorry, that's a redshifts for 1,000?
Yeah.
Right, okay.
And then you've got the added complication, they have to be in the DESI fields, right? So that, you have to throw away 2/3 of them or whatever, and it makes the Southern Hemisphere a little bit more challenging. But I mean, this is, with the rate that the field is producing, 1,000 FRBs is not, that's not 10 years, that's not 5 years away. It's not 10 years away. It's a few years away.
Okay, I see no questions in the room. Would you like to proceed?
Yeah, I guess it's my slide, right? So I'm actually working on strong gravitational lensing, and I think that FRBs also have a really good advantage here to break degeneracies, because I think that the best application for cosmology is to use FRBs to break degeneracies. And we used it in our own research to improve the estimates of galaxy cluster masses. Because normally when we use strong gravitational lensing to estimate masses, we usually have what's called the mass sheet degeneracy, or even worse, higher order degeneracies probing the small scale potentials in a galaxy cluster. And when we use the time delay that we can measure of one FRB, which is multiply imaged, then we can already improve the galaxy cluster masses by a lot. Because the time delay between multiple images of FRBs is more or less like to very high precision. And this means that all the uncertainty that you have from this is negligible compared to all the uncertainties that you have when you do the gravitational lens model and all this stuff. So you can say that the measurement is more or less very precise, and all your errors are in the modeling of the gravitational lens. And this is pretty good. So you can also hopefully get an H0 value, which is has a higher precision from FRBs. And this has been done by Lee et al. In a Nature paper. And you can also, Kelvin may be able to comment on that you can also detect small scale dark matter or black holes by interferometry in order to detect small scale clumps of dark matter or black holes by using FRBs, which are multiply imaged. And I think the most, futuristic application for this would be real-time cosmology. Because when you take multiply imaged FRBs, they have a very short time delay. And if you have repeating FRBs, you can measure these time delays over a certain interval of time. And if this time delay changes over the interval of time that we measure, we may be even able to get the dz dt. So like we can probe h of z using this multiple images of FRBs over a certain time interval. This has been done by Wugnitz et al. And by Citrine and Eichler. There are a lot of systematics in there, and it's very futuristic, but if it works, it would be quite interesting. So these are the possible applications. And of course, it's still in its infancy, and we have to take a lot of steps to get all the systematics and the uncertainties right. But I think that these are the more or less major applications that we can have for lensed FRBs. If you have more, I mean, we can discuss it. That's what came to our mind.
We had one question online, which was, what kind of follow-up strategy would you recommend for catching strongly lensed FRBs, specifically for galaxy lenses?
Oh, interesting. So what we have is, first of all, we need the redshift of the lens. I think we need the redshift of the source. So we need localizations. And usually if we have galaxies, we have a separation of 0.5 arc seconds. So I do not expect that we get FRBs in the spatial domain. So what we would need, we would have in the time domain, we should monitor how far these FRBs are lying next to each other in the time domain. It should be on the order of days or a week or so. So I would monitor the direction and then look if we have similar FRBs coming about a week apart. So cross correlations over time. But
the VLBI instruments will spatially resolve the lens, right? So they'll have each FRB, you will know where it is to, tens of milli-arc seconds. So you will spatially, the lens will be fully spatially resolved. And you can not only identify that the FRB is lensed that way, because you'll localize it to a smushed out arc of the lens galaxy, but then you will you'll know which lens arc it's come from.
Perfect. I was wondering whether they are already at this precision. Okay, fine. If localization is no issue, then we can also monitor in the spatial domain. I mean, this gives us even a higher confidence that we have actually a lensed FRB if we see two FRBs more or less predicted right brightness to be lensed, to be two images of the same, and then we have the time domain, and if we see a similar profile, this is quite good. So we have two criteria to find lensed FRBs for galaxies. So I think for galaxy clusters, it's a bit more difficult because there I expect the dispersion measure to be quite different. So they may not look alike in the time domain.
Yeah, this is actually something I was just wondering. So if you have a lensed FRB, they do go along different propagation paths, probably different DMs, different scattering properties to some degree. So I think the hard part is because you actually said they might be separated in time by order a week, did you say, I think?
Yes.
So, I mean, besides, I don't know, some sort of time structure profile, how do you actually make sure you are seeing a lensed version of it? Of course, you can see, okay, it's left and right of a certain galaxy. So that's probably an indication that it is a lensed image. But then if they do have different scattering properties within, I don't know, how many different DM units, depends on the contribution of that, whatever is causing the lensing.
Right.
It's not going to be too easy to then actually say, okay, this is a lens or this is something else, I think.
Well, I think it can be quite easy because you have a host galaxy, and this host galaxy will also be multiply imaged. And this is also a big advantage for FRBs compared to quasars, because the FRB is just a shot event, and afterwards you will see the host galaxy again in its natural form. Compared to quasars, are bright and shiny, and you have a hard time to disentangle the bright and shiny quasar from the host galaxy. And the host galaxy gives you resolved information about the multiple image position as well. Usually you use it to model the galaxy scale lens. And so you can identify the FRBs if you also have multiple imaged host galaxies.
Okay, another question from me in JMA. And so you have mentioned that this can use to improve the mass estimate of lenses. I wonder because I wonder that for strong lensing systems, things like Holocaust or TD Cosmos, they do obtain multiple images of a background varying stars or variable galaxies. In your case, do you need to have those samples which each of the image that absolutely corresponding to your delay measurement, or you could have a different delay measurement, but for the same background galaxy that you still can use the data to constrain. Am I clear? Or?
So do you mean you have a quasar and an FRB, or?
Yes, I mean you have a background variable galaxies and you have multiple images, right? Do you have to make sure that your FRB time delay measurement also have the same light paths of those different images?
Yes, yes. I mean, if the FRB is not related to the multiple image galaxy that you think is the host, I mean, then you have an issue. I mean, you just need to know the to which host the FRB belongs to. And then you model the host galaxy, you use the host galaxy to model the strong gravitational lens, and you use the time delay from this host in order to get to H0 or to something else, to the mass estimate.
So this will have a pretty precise measurement of the gravitational potential? That
Yes, yes. So we made it for galaxy clusters because I'm more interested in galaxy clusters. They are, I mean, more messy, and therefore you have to model a lot, while galaxies have an easier profile to model. So I thought the galaxy clusters, if we have masses which change in this galaxy cluster by 10 to the 5 solar masses, we can measure this by comparing the time delays for 2 different time intervals in such a scenario. So we measure the time delay and we get a mass for the cluster. And if the mass changes by 10 to the 5 solar masses in a certain time interval, we can measure this if we measure the second time delay of a fast radio burst. So we are very, very sensitive to the mass, to changes in mass.
okay, yeah, that seems to be interesting.
Yeah. And I think it's much more interesting to constrain the masses and to get a better idea of what the gas distribution is in these galaxies and galaxy clusters instead of going to H0. I mean, I would say we have no idea where the gas is and where and how this how the interplay is between dark matter and gas, and having multiple images of host galaxies and FRBs tells us a lot about the interplay between gas, dark matter, and luminous matter.
Yeah. I mean, certainly that is something very interesting. But to decouple the Fermat potential from the delta T time delay to deduce H0, that phi need to be pretty well measured. And I'm just worried that FRB may be only sensitive to the gas, which is pretty light compared to the underlying dark matter. So maybe the
yes.
Yeah.
I mean, in the end, actually, I mean, what's driving the H0 in strong lensing is totally the kinematics, because the kinematics breaks the mass sheet degeneracy, and without it, I mean, you can't do much.
Absolutely. Yeah. Thank you.
Yeah.
Okay, I'm gonna ask that we finish this now because we're at the end of our time and the coffee break is coming and a reception is coming. So thank you all. We'll have a second, there's a 1B discussion tomorrow morning in which we can continue this topic. So, but thank you all for your contributions today.
Thanks for the invitation.
And thank you to those who stayed up late or got up early.